This is the development view as well as the third-person view of a field test of the Fulcrum robot using the vision software. So just to explain the suite a little bit, here's the pointer with the red dot. This is just a lot of verbose text output for the vision model that's happening here, and very little bit about environment, like um, the frames per second, the counter, seconds, and variables, which is not going to be accurate because I'm slowing everything down by talking about it. This screen over here shows a little bit of information about light, like the percentage of lux, whereas 1% or less would be indoors and 100% would be the brightest sun recorded. These pixels here are just basically showing you that in the dark blue, that means that the low pixels 0 to 127, there's more of them since this red line is the halfway mark, than the high pixels, which is 128, 255, which is the light blue. So that just moves back and forth to tell you. This is a histogram bar graph of the histogram of the image, and the lines here are output from the algorithm that I can see that's running to show me what's going on. Here's another Lux view, and this is just the front, the back, the left, and the right. And they show the raw Lux numbers in on top, and the B is yellow and bold because it's less than 50% lux intensity, and the most intense it's picking up is from the back. So the rear of the robot's getting where the light source is coming from, which is also denoted in the color image here by the yellow and black dot. Now over here, the low and the high are two different images, again, that the algorithm generates, so I can see which of the two is actually happening and making sense as I'm developing the algorithms. These two are just added together for ResF over here to the right, the final result, which is then used to show to create the symbology that's used in D out, which is the color image here. This line is called the horizon line. When it's green, it's just slightly sending commands to the robot to slightly move away from the red, black, and blue dot, which is the obstacle of most importance. If you see the horizon line go red, you should see the robot down here totally stop and then like use both wheels to turn like on a dime about the center of its chassis, which we would call a sharp turn. If it's green, it's a shallow turn away from the obstacle of most importance. This blue, black, and white is called the clear path, which is turned off right now, so you can just go ahead and ignore that. What I'm going to try to do is I'm going to try to start the video here, and we'll look at the robot. We'll see the lux sensor turn up on the top of the robot here, which means it's about to start. I'm going to try my best to synchronize the replaying of the image data with the video, and we'll go ahead and see how well I do on that, which is really my thing. So we'll look for that lux sensor to pop up. Now he's about to start, so we'll go ahead and hit start on the development environment, and now you see the lines moving. And if you see a box down here towards the bottom, which is blue and gold, that basically is what it thinks the robot shadow is, which you see a lot of failures in that system right now. Coming up on this tree, but it's not really being detected at all. I'm going to slow it down a little bit because I can tell it's already getting out of this. So see that sharp turn away is what we're looking at now. And it's a lot of erroneous information here as it's not really detecting the good features of the rock. But you'll see how it gets close just enough to turn away and then take a look over here, which these rocks are all right. You can see in the high and the low what features are being picked up, but again, it's not perfectly accurate. Now we're going towards the camera, you can see, so you can see this tripod in my backpack here. And there's me, so we're kind of going along with it. And it's an early morning, hence the shadows being cast, which is the environment I want to test the algorithms in because it's harder than direct over sunlight, which is kind of easy to write vision software for. So you see that quick turnaround. And then when he's coming towards the bricks here, you'll see that the low features, the dark, are really what's picking that up to make it not just drive off this panel, because the brick is basically the same color as the ground, the drivable ground area. And then you can see it turn right around away from that and keep going back. But this is basically how I develop the algorithms, by replaying the data during the field test and compare with, me being a human, how like a human, with moderate intelligence or a simple animal would move around. And you see a lot of noise, a lot of errors here. So then I'll fine tweak certain variables in the algorithm, which is, this is all going very fast, and a lot of that stuff is confidential, so I won't be covering it in detail how all that stuff happens. But this is an algorithm that's all right, but by no means close to perfect. So it'll take a lot of work on it. But we'll see here where things are starting to fail, because if you know the robot shadow, if you notice in ResF, that contour will be blacked out, which means you can't have an obstacle inside the robot shadow, which is not good logic because, like you're going to see, it's going to start blacking out some of these rocks that it rolls up on. The shadow goes over the rocks. So it's not great by any means in terms of logic to pick up these obstacles, and you'll see them start to happen pretty soon with these rocks. It's going to start missing some rocks that are quite large. Let's see if I can pause both of them relatively at the same amount of time, where it's kind of an interesting data set. And it just gets, and here's where it fails. So actually the video is a little bit behind. My bad. So he turns towards that. That's basically where we are. So as you can see, the shadow is casting over this obstacle, this rock. So it's blacked out that entire contour. That's not good. But this bright spot, which is not under the shadow, the dark shadow, it's not even being detected by the high version of the algorithm. So that's no good. Top right corner, you'll see an obstacle here, which corresponds to this bright rock over here. Um, so it's definitely seeing that. It's seeing this one here, which is this guy here, which is that guy there. But the one directly in front of it, which also has some of the shadow cast over it, is not being detected, and partially due to, well, I'm sorry, partially due to the, oh, actually, it's wholly due to the algorithm just failing. This is a bad algorithm. But it's not part, this failure is not part of the robot shadow, because see how the box, it's not seeing that shadow as shadow. It's just below that it's blacking out. So it does see a little bit of a dot here, but not enough to make a difference. And that's the big failure. And I'm pretty sure this is the rock that it comes in contact with and fails during the run. So we'll just take a look here and see what it looks like when it comes up and fails. So see, he's already hit it. It's already hit. And this is a failure of the robot shadow detector because it's not detecting the robot shadow. We don't have that. Well, actually, I'm sorry. It detects it down here. The blue and yellow is detecting this, not the actual large robot shadow. So you can see that all of the dark pixels, the low pixels, are showing up as obstacles. It just thinks this is a big dark object instead of us knowing that this is just a dark shadow over little tiny objects. And either way, this rock right here is not showing up anywhere. So it's a huge failure. We got 1, 2, 3 rocks here. Only one's being detected, the brightest one. There's a little tiny detector that doesn't matter closer there, but what you do, this is bad. So that's basically how it rolls through a development cycle. And with the third person view, you can kind of see what it looks like when I'm out there doing a field test. So thanks for watching.